Hello everyone. Today we are going to discuss the problem Giant Pizza from CSES Graph problem set. Let's go through the problem. Olive's family is going to order a large pizza and eat it together. A total of n family members will join the order and there are m possible toppings. So the pizza may have any number of toppings. Each family member gives two wishes concerning the toppings of the pizza. The wishes are of the form topping X is good or bad. Your task is to choose the toppings so that at least one wish from everybody becomes true. A good topping is included in the pizza or a bad topping is not included. So the first input line has two integers n and m, the number of family members and toppings. The toppings are numbered 1 to m. After this, there are n lines describing the wishes. So each line has two wishes of the form plus x that says that topping x is good or minus x that says that topping x is bad. So you have to print a line with m symbol. So for each topping, plus if it is included and minus if it is not included, and you can print any valid solution. And if there are no valid solution, you can simply print impossible. The number of family members and toppings are of the order of 10 power 5. So let's first of all try to understand what the problem is, and then we will see how we can actually solve this. So just copying this input example over here, we have 3 family members and 5 pizza toppings, and these are the wishes of each of the family members. So we have just took a valid arrangement of toppings where we are not including topping 1 and we are including every other topping. Let's see whether it satisfies the condition that at least one wish of every family member is fulfilled. So we are not including topping 1. So let's see what are the wishes that are not getting fulfilled. This particular wish does not get fulfilled, right? Rest all other are fulfilled. Topping 2 we are including. Any wish that is not getting fulfilled? This particular one, which says that topping 2 should not be included. Third is getting included. No issues. 4 is getting included. Again, no issues. 5 is getting included. Again, no issues. So with this particular toppings arrangement, you can simply see that at least one wish of every family member is fulfilled, and therefore this is a valid arrangement. If there is if there does not exist a single arrangement in which at least one wish of every family member is getting fulfilled, in that case you have to simply print impossible. So this is what the problem is. I hope the problem is clear to each and every one of you. So let's see how we can solve this. So before moving ahead with the problem or the solution to the problem, I want you guys to already know what is the meaning of SCC, that is strongly connected components. So if you are solving the problems in order from the list, and if you didn't knew this and if you watched a video, one of my videos, I have explained this SCC in detail. It might be a slightly bigger video, but I have explained in detail like what this SCC means and how we can actually find SCC in graphs. So you can refer to that video, and if you know from before, no issues, you can just continue watching the solution. So this is going to be the prerequisite for this particular video, because this particular problem itself involves a very important concept along with SCC. So I don't want you guys to focus on two important concepts at once. So SCC is going to be the prerequisite for this particular video. Okay, cool. So how we can actually solve this? So to solve this problem, we should know a very important concept of SAT. What does SAT means? I hope many of you would have heard this before. Boolean Satisfiability Problem. SAT is a Boolean satisfiability problem where you will be given a Boolean formula and you have to assign some values to the variables such that that complete Boolean expression returns as true. It is basically a conjunction of clauses. So basically you can see over here, if I just write a CNF form, this CNF, the full form of CNF is conjunctive normal form. So if I simply write this, Let me write a clause. Let's suppose A or B. Another clause as A or B or not C. Another clause as A not or not C. If I write this particular clause, so Boolean satisfiability problem is assigning some values to variables A, B and C such that the value for this particular expression returns as true. So this is what the Boolean satisfiability problem is, but this Boolean satisfiability problem is actually NP complete problem. This means there does not exist any known efficient solution for this. So no known efficient solution. But there is a variability of this, like there is a problem called as two-sat problem, which is just a slight modification of sat, which can actually be solved in finite time, and the time it actually takes is big O of n plus m, where n is the number of variables and m is the number of clauses. So what does two-sat says? Two-sat says that any clause can have maximum of two variables. For example, in the above example that I took, if you just notice, this particular clause has three variables, right? This particular clause has three variables, so this does not come under two-sat problem. Rest, this particular clause and this particular clause, both of them has two variables, so no issues with this. So two-sat says that any clause can have maximum of two variables, and if this is true, then we can actually solve that problem in finite time, that is in big O of n plus m time, where n is the number of variables and m is the number of clauses. How do we actually solve this? That we will definitely see, but this is what the two-sat says. Okay, now how we can actually solve this? So to solve this, I will just take an example. I've just copied it from internet. So you have a CNF form. Let me write a CNF form for this. So you have this particular expression, A or not B, and not A or B, and not A or not B, and A or not C. So this is the CNF form. So to solve this, first of all, we need to convert it to implicative normal form. So if I just convert to implicative normal form, I'm just writing down these words. Actually, this concept is not very tough, but to make you guys completely understand all intuitions and all, I'm just writing down all these words as well. So how to convert it to implicative normal form? So basically, if I say you that I have an expression A or B, how I convert it to implication? I can write it as not A implies B and not B implies A. That is, if any of A or B is false, the other should be definitely true. This is what it says. So if any of A or B is false, the other should be definitely true, because I want this as true, right? So this is how we will actually convert it to implicative normal form. So let me do it for every clause. So if I just write it for A or not B, we can write it as not A implies not B and B implies A, because not of not B becomes B. So B implies A. Similarly for this, we can write it as A implies B and not B implies not A. Again, for this, if we write, we have B implies not A, and A implies not B. And for this, if we write, we have C implies A, and not A implies not C. Okay. So now if we convert it to implication graph, how we will convert it to implication graph? So if we have that A implies B, we will do something like this. From node A, we will have an edge to node B. So you will see that for every variable A, B and C, we will have, like, for every variable there are two nodes, that is A and not A. So in total, we have three variables over here, right? So we will have 6 nodes in total, that is A, B, C, and not A, not B, not C. So let me just draw this all 6 nodes. So over here, C is only with A, so A not A. Okay. So let me just name these variables. Let me name this as A. This as from A you have to C to A. Okay, C. Then this as not A and this as not C. This as B and this as not B. Okay. And let me just draw the edges between them. So edges look something like this. From C you have an edge to A. From not A you have an edge to not C. From A to B. From B to A. From A to not B, if I'm not wrong. From A to not B. Okay. From B to not A. From not B to not A. Not A to not B. And yeah, all the edges done. 1 2 3 4 5 6 7 1 2 3 4 5 6. Okay. So this is how the implication graph looks like. This is how the implication graph looks like. Okay. Now looking at this implication graph, one thing is very much clear. How we can verify whether this graph is correct or not? You know that if A implies B, then by contrapositive, we can also say that not B should imply not A, right? By contrapositive, we can say this. You can verify this from graph. If we have an edge from A to B, we also have an edge from not B to not A. If we have an edge from C to A, we have an edge from not A to not C. So yeah, this graph is actually correct. Okay. Now just say me one thing. We have to check whether we can actually solve this two-sat expression, this two-sat problem or not with this particular expression. We need to verify that, right? Just say me one thing. If you have some variable, let's suppose I take an example of variable X, or let me take an example of variable A. If you have some variable A, if I say that A is reachable from not A, sorry, A is reachable from not A. If I say something like this, what does this mean? This means in the graph, you have some set of edges such that if you start from A, you will end up at not A. This means, right? This means that, or A is reachable from not A basically means that if you start from not A, then from some set of edges, you will be able to visit A. This means that not A was implying some variable x1, x1 was implying x2, and x2 was implying A. Something like this, right? That is, if you start from not A, you will be able to visit A. Something like this, right? So if this is the case, that A is reachable from not A and not A is also reachable from A. A is reachable from not A and not A is also reachable from A. If this is the case, can the solution be possible? Can the solution be possible? Just imagine. By this, we are meaning that A implies not A by induction. By induction, we can say that over here not A implies A, right? So similarly for this, we can say that not A implies not A and not A implies A. A is reachable from not A and not A is also reachable from A. So we can say this thing, right? Can this be possible? Can this be possible? Just think. Because if we, let's suppose, assign the value A as true, if I assign the value expression A as true, then this is never possible, because if A is true, then not A should be true, but for not A to be true, A should be false, but we have kept A as true, so there is a contradiction, right? No issues in this, because if A is true, then not A is false, so false can't imply anything. So basically, if A is true, then we are getting contradiction over here. Similarly, if we assign A as false, then this particular thing, not A, will be true. This implies that A should be true, and for A to be true, but we have assumed A to be false, so there is a contradiction. So we can't assign A as true, we can't assign A as false. Both of these are not possible. Both of these assignments are not possible, and hence in that case the solution won't exist. So from this graph, we have to first of all check that there are no two variables, variable such that it is reachable from its contrapositive and its contrapositive is also reachable from it. Not contrapositive, sorry, negation. My error. That its negation is reachable from it and it is also reachable from its negation. For example, it should not be that A is reachable from not A and not A is reachable from A. These cases should not exist. So in directed graph, when do we say this? Now the interesting part starts. In directed graph, when do we say this, that okay, A1 is also reachable from A1 is reachable from A2, like A2 is reachable from A1 and A1 is reachable from A2. If this is the case, what does we say? We say that A1 and A2 forms a part of strongly connected components, right? I hope you guys know strongly connected components, basically a cycle in a directed graph. If A1 is reachable from A2 and A2 is also reachable from A1, in that case, we will say that A1 and A2 form a part of strongly connected component. So over here, in this particular case, first of all, we will divide this complete graph in strongly connected components. So let me just do that. Let me use this particular color. Okay. So as I can see over here, this is one strongly connected component. This is the other strongly connected component. Okay. This is one strongly connected component. And this is the other strongly connected component. So in this particular graph, we have in total 4 strongly connected components. And in all of these connected components, we don't have any variable. Such that in the single component, both the variable and its negation exist. Right? So definitely we have some solution for this particular expression. Okay. So this is verified that first of all, we found the strongly connected. First of all, what we did, from the CNF form, we converted to implicative normal form. From that, we formed the implication graph, and from the implication graph, we formed the strongly connected component. And then we verified that okay, there should not exist any strongly connected component such that inside the component you have both the variable and its negation. Because if that is the case, then the solution won't exist. So in that case, the answer will be impossible. Okay, cool. Now what next? The other thing is that okay, answer is possible, but how would we assign the variables? Because if you just look over here, if I assign the value of a as true, if I assign the value of a as true, so if you just look from here that a implies not b and not b implies not a. So you can actually say that a implies not a. So in this case, if we assign the variable a as true, this means left hand side becomes true. So right hand side should be definitely true, but right hand side can't be true. Because for right hand side to be true, you want the value of a as false, but we have assigned a as true. So you have to carefully assign the values, right? So what I want to say over here is that there may be the cases where, let's suppose, either x implies not x or not x implies x. They won't exist simultaneously, like it won't be that both of the cases exist, but it may be that at least one of them exist. Not, there may be that both does not exist, or it may be that one of them exist. Definitely both won't exist together, because if both exist together, we have already discussed that case. In that case, the answer will be impossible, right? Cool. Now just say me one thing. If this case is existing, in that case, what value to this variable x would you assign? Just tell me one thing. What value to this variable x would you assign if this particular case is existing? That is, not x is reachable from x. In that case, you would assign the value of variable x as false. Right? Because if left hand side becomes false, then there are no issues. Similarly, if x is reachable from not x, in that case, what you would assign your x? You want the left hand side to be false, right? So in that case, you want not x to be false. So in that case, you will assign the value of x as true. So if any of these cases exist, because we don't know that whether which of these cases are existing or not existing, we are not aware of that, right? So we have to be very much clear with this, that okay, if it is existing, so your assignment should not lead to contradiction. Like in this case, if you would have assigned the variable x as true, then the contradiction would have arrived, right? Because left hand side would have become true, so your right hand side should have been true. But for right hand side to be true, this x should be false, but you have assigned x as true, so contradiction would have been there, right? So you have to be very careful while assigning the values. So now the question comes is that okay, the solution exists, but how should we assign the values so that there are no issues in solving this? So before discussing that, I will also discuss one more thing, that why x implies not x and why assigning x as false won't face any issues to you. Let me just elaborate this a bit. So what I am saying is, let me take this case, not x implies x. If not x implies x, okay, this case exists. And if I am marking x as true, okay, I'm marking x as true. So I'm definitely sure that now this thing, not x implies x, is not an issue for me, right? Now let's suppose there exists some variable y. Let's suppose you have node x over here, and there exists some variable y such that y is also reachable from x. Okay, we can skip this part actually. Just saying. Okay, let's suppose y is reachable from x and not y is also reachable from x. So this is actually y, and this is not y. And I am saying that not x is reachable from not x. Don't get confused over here. I'm just explaining why assigning x equals to false in this case won't face any issue for me. This is the case. So we have already discussed that if x implies y, this says that not y should imply not x. So in this case we will have an edge where not x is implying x. So we will have an edge that we will have an edge from y to not x. We will have an edge from y to not x, and we will have an edge from not y to not x. Okay. And if this is the case, then not x and x will be the part of same strongly connected component, which can't be true. So basically what I want to say over here is that if x is reachable from not x, then there cannot exist any variable y such that both y and not y are reachable from both y and not y both are reachable. Not x is reachable from both y and not y. This case can't exist. Okay. So if this can't exist, so definitely that won't form any issue for you by assigning the value of x as true. So this case won't form any issue for me, right? So basically what you have to understand till now is you have formed the implication graph, then you formed a strongly connected component. In the strongly connected component, you can't have any variable such that both the variable and its negation exist inside the same component. Next, there may be the case where either the variable is reachable from its negation or the negation is reachable from its variable. So we have to be very much careful while assigning the values to the variables. So while we are assigning the values, we have seen that how we will actually assign the values. If not x is reachable from x, in that case we will assign x as false. If x is reachable from not x, in that case the assignment of x should be true. Cool. So now from the graph, how will we actually do this? So if you guys remember the solution of strongly connected components, what I told is the strongly connected components are ordered in the topologically sorted order. Strongly connected components are ordered in the topologically sorted order. So let's suppose after strongly connected components, what you get? You get vector of vector int of components, right? So let's suppose you got this thing, SCC1, strongly connected component 1, then SCC2, then SCC3, and then SCC4. Let's suppose you got these 4 components in your strongly connected component. And let's suppose I have this thing that I have an edge from, let's suppose x to not x. That is, x implies not x. Not x is reachable from x. I have this thing. So what I'm sure is not, if let's suppose not x is part of any strongly connected component I, and x is part of any strongly connected component j, then this value j will definitely be lesser than I. This I am pretty sure of, right? Because what happens in strongly connected component, if you have an edge from u to v and these are not part of the same strongly connected component, then first of all you will get the strongly connected component for u, and after that you get the strongly connected component for v. This will happen, right? Because we arrange it in the order of t out, decreasing order of t out time, and at least one of the nodes for that SCC what we take the maximum t out time of all the nodes, and then we do the topological sorting, right? That eventually happens when we follow the order of topologically sorting order. So if we are doing that, we are pretty much sure that if there is an edge from x to not x, then the SCC for this x will come before the SCC of this not x. So we will know for every variable, we will know what component it belongs to. We can assign the component for each and every variable, right? So we will know what component it belongs to, and according to that, we can do the assignment. I will explain this with the help of this particular example. Okay. So let's suppose I am naming this first component as 1. So this node C will get the value as 1, or component number as 1. Then I am saying this A and B will get the component number as 2, not B and not A will get as 3, and not C will get as 4. So let me just write what are the components for each and every node. So you have in total 6 nodes, right? You have C, then A, then B, then not A, not B, and not C. These are the 6 variables that you have, right? So C, the value for C is component number is 1. For A and B it is 2. For not A, not B it is 3. And for not C it is 4. This is what you have, right? Okay. So now how will I assign the variables? Let's first of all assign by order, okay? For A, we will assign true or false. For B, we will assign true or false. For C, we will assign true or false. We'll see that. Okay. Coming to A, what we will see first is the component number for A and not A same. For A it is 2, for not A it is 3. So definitely the component number is not same. Check passed. Now what should we assign, A as true or A as false? So we can see that the component number for A is lesser than the component number for not A. This means there might be, I am not sure, by looking at this particular component numbers, I am not sure whether there definitely exists a path from A to not A or not. I am not sure of that. But there might be the case that there exists a path from A to not A, which implies that there might be the case that A is implying not A. This can't be true. Not A can't imply A. This I am pretty much sure by looking at this component numbers. But I am not sure whether this case exists or not. So just be in the safer side. For this case, if this case was there, what I would have assigned A? I would have assigned A as false, right? So just for being in the safer side, I will assign the variable A as false. Similarly for B, the component number of B is 2 and the component number of not B is 3. So there might be the case where B is implying not B. There might be the case, right? So in this case, I will assign the variable B as false. Similarly for C, if you just look, C, component number of C is lesser than the component number of not C. So in this case, again, I will assign C as false. So by assigning all of these 3 variables false, let me see what answer I get to this CNF. The first one is A or not B. So that becomes true. And not A or B, again that becomes true. And not A or not B, again that becomes true. And A or not C, again that becomes true. So you can clearly see that by assigning all of these variables A, B and C, the value false, the expression returned as true, and hence you were able to solve this problem. So if I just summarize what we actually did in this particular problem, we are first of all converting the CNF form to implicative normal form. From that we are getting the implication graph. Then we are finding the strongly connected components and assigning component number to each and every node. And then we will see what value will be assigned to every node. So while assigning the values, we are also checking that whether the component number for the node and its negation is same or not. If it is same, we will simply return impossible, that the solution is not possible. But if they are not same, then we are assigning value true and false based on the component numbers. So this is how actually you are going to solve this problem. So in the problem, if you just look, what you have you have these many number of family members having two choices each, right? So the choices will become actually your clauses. Choices will actually become your clauses. Like, let me explain with this: +1 +2. So if I am saying that's 1 as variable a, 2 as b, 3 as c, 4 as d, and 5 as e. So +1 means you want a, +2 means you want b, and at least one of them should be true. So a or b should be true. The second one says that I don't want a, but I want c. So this should be true. The third family member says I want 4, I don't want 2, that is b. So this D or not B, because we want at least one choices to be true. So any one of them being true will do the case for me. So the CNF for this particular example will be A or B, and not A or B, and D or not B. So if you simply solve this, you will be able to solve this problem, right? So let's see the code for this. You will understand the things better from there. So before solving the code, I will just tell you that this is the code. This is the helper function I have for finding the strongly connected components and returning the component number. So this entire code is for finding the strongly connected component, where first of all, this n is the number of node, m is the number of edges. So from edges, I am forming graph and reversed edges graph, then doing the topo sorting and going over this and forming the components, vector of vectoring components. Once I am able to form this component, I am just keeping the variable of count 1, answer of size n, and going over every component. So every node in a particular component is assigned the same component number. And once I am done for assigning for one component, I am increasing the count. So by this, I am basically assigning the component number to each and every node, and I am returning that. I am not discussing this particular code because I have already discussed it in the video that I have shared for SCC. So you can definitely look through that. So that is actually a problem only where I have explained the concept of SCC very well. So that is the exact code. I am using the exact code over here. Okay. So basically, I just want to say that this is a helper function that will help you to get the component number for each and every node. Okay. Now let's see through the question, this code for this particular solution. So I am taking variables m and n as input. So m is basically the number of family members. In the question, it is given reverse, like you are given n and m, but I have taken input like this so that we don't confuse the things. So I am taking m as family members and n as the possible toppings. So basically n is the number of variables and m is the number of clauses. I will come to this later. Then there are sign 1, sign 2 and two nodes u and v, and I am taking the input in edges pair of int, int. So going over every clause. So clauses are given, how the clauses are given: first of all sign, then the node, then for another choice sign and the node, converting the node to zero based indexing. Now just say me one thing: if sign 1 is negative, this means what I want a negation of this u, right? So I am converting this u to its negation. If sign 2 is negative, I am converting this v to its negation. Now what does negation means? So if you just look, for every node a, you also want its negation, right? Now how will I represent this node like this? Let's suppose I have node number 0. How would I represent a negation? So there are multiple ways that you can follow. What I have done over here is, you have nodes numbered from 0 to n minus 1, right? Because there are total n toppings. So I have numbered the negations from n to 2n minus 1. Okay. So basically the negation for 0 will be n. The negation for 1 will be n plus 1. Negation for 2 will be n plus 2, something like this. Also, we can say vice versa. We can say vice versa as well. That negation for n will be 0. Negation for n plus 1 will be 1. And negation for n plus 2 will be 2. So how I am writing this negation logic? So I am taking the node as input. If the value of node is greater than equals to n, then for finding its negation I am subtracting n from the node. And if its value is lesser than n, so for finding the negation I am adding the value n to this node. This is how I am finding the negation. Once I have found the negation, so what you have now, you have the choices, right? Let's suppose you have the choice A or not B. So you have to convert this to the implicative normal form, right? So you want this thing. First of all, not of A implies B, and not of not B, that is B implies A. You want this thing, right? So that I am doing. In my edges, I am pushing back negation of V comma U, that is edge from negation of V to U, and also edge from negation of U to V. So these are the two edges that I have. Then I am getting the component numbers by passing the inputs to this helper function, where the total number of nodes will be 2 into n, because for every node we have the node and its negation, right? So total number of nodes will be 2 into n and the edges. Then I have this assignment variable where I am assigning the values for the particular variable. So I am going over all the variables from 0 to n minus 1. If the component for that variable and the component number for its negation, if they are same, in that case I am simply printing impossible and returning. Otherwise, what should be the assignment of I? Assignment of I will be either 0 or 1. 1 means I am taking that node, 0 means I am not taking. So basically, if component of I is lesser than component of negation I, what does this mean? This means that there might be the case where x is implying not x. Component of x is lesser than the negation. So it might be the case that x is implying not x. So in that case, I will assign x as false. So if component of I is lesser than component of negation of I, in that case, assignment value is 0. Otherwise, it is 1. So once you are done with this, go over all the assignments. If assignment of I is true, add plus, otherwise add minus. So this is how you can actually solve this problem. Again, a very, very important concept, a very good concept as well to learn. So I hope all of you understood it well. Thank you.